Most of my research is focused in East Africa. We're trying to understand how complex terrain in East Africa is changing because people are expanding agriculture, there's urban growth, and many other factors that change the surface dynamics. I'm Nathan Moore. I'm an assistant professor in geography. I do climate modeling, and I'm trying to integrate climate change and impacts with land use change and agricultural modeling. Those changes in surfaces impact the climate both locally and regionally. We're trying to understand how those changes might affect the weather and ultimately food production in the next 10 to 20 to 30 years. The problem with doing these predictions is A, we cannot predict the future very well, and B, we can't integrate climate change and agricultural modeling very effectively yet because there are other factors besides weather that influence crops. For example, economics. For example, land tenure and land ownership. So we're taking this from more of the physical perspective side and trying to understand at least what are some of the constraints that a hotter or drier or wetter climate might impose on the extent of agriculture that we can pursue in East Africa. I also work in the Amazon looking at changes in deforestation and expansion of soybean farms to try to better understand if the large-scale circulation of the Amazon basin is being changed by changes in land use, by modification of the land surface. Finally, I've been doing some work in China to try to understand how top-down government policies have altered the structure of the landscape. We want to understand how removal of forest and transformation of some of the best agricultural land on the planet into cities is changing temperature, water flow, and other factors that are vital to the survival of China at the very time that it's increasing its pressures on the environment. Climate models are three-dimensional cubes of atmosphere. I simulate about 1 million points in the air, and I solve equations of motion, conservation of heat and momentum, and so forth for every point. That's a huge computational load, and HPCC has been very good at providing us a basic framework to not only get all the data on there to run the models, but to actually do the processing in a quick and timely fashion, to do simulations at resolutions that were really not available 5-6 years ago. And in addition to doing these intensive climate simulations, I also have to do crop simulations, and so that we've been working on developing code onto the HPC to simulate crops. And the flexibility and the ease of getting other students onto the HPC has been really good at replicating experiments, trying new perturbations, and trying to really find out where is that boundary in the physical world. Where should we be looking for? If you have the computational power, you can really diagnose the physics of the system pretty well.